Hello everyone, it's great to see you guys joining early. Stay tuned, we'll be starting shortly. Hello everyone, welcome to another session of Data Art series. We'll be starting shortly and let's go get to know each other in the start and I'll be launching a feedback poll for that. Thanks everyone for joining us today. We'll start the session in 2 to 3 minutes. Hello and welcome everyone to another session of Data Art series. I'm Chadan, part of the data science team at Analytics Vidya. For those who have joined us for the first time, here's a brief discussion about the 8-hour sessions that we have been conducting. The Data Hour is a series of webinars which is conducted by Analytics Vidya and led by top industry experts. It is a fun way to understand the concepts of data science. Now on to our session today, which is From Digital Twins to World Models, the Next Frontier of Industrial AI. Now, before we get the things started, here's a quick recap of the things that we have been doing. We are recording this session, and the recording will be available on our events page. Please use the Q&A section if you have any question in your mind. We'll be sharing a feedback poll in the end. You all are requested to fill that poll. Now, on to our speaker. In this session, we have Ankit with us. So, Ankit is a data scientist at Ascent Systems, focused on applying AI to solve real-world business problems. Okay, guys, so thank you for your patience. Now, over to you, Ankit. The virtual stage is yours.
Thank you. Let me share my screen. Once it is visible, just let me know.
Yes, Ankit, it is visible.
Okay. All right, everyone. Welcome. Thanks for joining today's data hour. I know you have a million things competing for your time on a Friday evening, so I really appreciate you being here. So, good evening and good morning, everyone. So, today we are going to talk about something that I have been digging into deeply for the past few months. And the more I research it, the more I'm convinced. So, this is going to be one of those things. So, we look back and say, yeah, that is when everything changed. So, we are going to talk about the shift from digital twins to world models. And I know that sounds like a lot of buzzwords, but stick with me. By the end of the session, I think you will see industrial AI in a completely different light. Let's get into it. So before we start, I will love to give a quick intro. So I'm Ankit Hemant Lade. So I'm a data scientist. I have like more than like 5 years of experience. So I've been working across a few companies such as like Ascent Systems, Radial, Native Agtech, Grad Dreams Education Consulting Private Limited. So my thing has always been taking technology and figuring out how to actually solve real world business problem with it. So I love jumping across different industries. Like I'm very honest with you guys, the same problems keep showing up everywhere. But now I have like any of you have seen my last data session. So we talk about time series forecasting. So we went from Arima all the way to Morai. So which is a foundational model for time series. So today is actually the next part of that story. So last time it was like foundational models for time series. This time foundation models for the physical world. So it will make sense as we go through. And I'm also a researcher, so I have like published few papers. So if you're interested, you can ping me and then I can share you the links. Thank you. So let's begin. So here is what I'll be covering. So we'll start with the big picture. So why this matters right now, and who is making massive bets. Then we'll build the foundation. So what digital twins actually are, what they are good at, and honestly, let me like where they fall short. There are like two real world use cases. Like we will go over like BMW and Foxconn, just for your information. So these are like real world use cases, but I have like simulated few of those, and then I have created a small notebook so wherein we'll go together and then we'll understand. And then the exciting part, like we'll probably define world models, how they learn physics, and we'll actually go under the hood on the architectures of Genie 3, Cosmos, Mamba versus Transformers. I know some of you are like technical, so I want to give you enough meat to chew on there. So three more use cases after that, and then I'm going to be real with you about the challenges, what doesn't work yet, what is still risky, because I think honesty makes the whole conversation more credible. And then at the last, we'll finish with ROI numbers, the tech stack, and a practical playbook. And I'll leave plenty of time for some question answer. Any question for the table of contents? If no, we'll move to the next slide. Okay, so let me start with the question that got me obsessed with this whole topic. So we all have watched what happened with language, right? Like GPT came along, like there were like lot of trends, different tools and technology started coming into the market. Then Anthropic launched, like a lot of things are there. And then we also trained on a like huge amount of text, and suddenly AI could write reason, have conversations. So nobody really saw that coming at that speed. So at the same time happened with images, like there were like stable diffusion, mid journey, trained on billions of pictures, and now you type a sentence and get a photorealistic image. So here is the question I kept asking myself. So what if AI could do the same thing with physics? What if could learn gravity or friction or momentum? Not because some engineer spent 6 months writing different equation, but because it just watched the world, observe enough data to figure it out on its own. So that's the world models are. So that is literally what they do. And the reason I say this is the inflection point, it is because five things are lining up at the same time. GPUs are 1,000 times cheaper than they were 10 years ago. Foundational models have crossed the quality line. GPT-4, Claude, Gemini, they actually work now. Open USD standardization, 3D data, so different tools can finally talk to each other. Edge hardware is like powerful tool enough to run interference right on a factory floor. And there is over 3 billion euros, billion with a be flowing into models just in 2025 and 2026. So when we have like five of those things happen at once, that's not a trend. It's a paradigm shift. And I'll also move from Jupyter Notebook. So let me show you some Jupyter Notebook. So what I was talking about, like five forces converging. So the GPT movement for the physical world. So LLMs learn language from text, diffusion model learns images from pixels. So world model learns physics from data, and then five forces across converging now. So GPU compute like 10,000 cheaper than a decade ago. Foundational model crossed the quality threshold. OpenUSD standardization 3D data exchange. Edge Harvard powerful enough for factory interference. 3 billion invested in world models in 2025-6, and then which was done by Len Kun, DeepMind, and Jensen Huang, all the bet on the same thing. It happened. Let me move to the next slide. And before you think this is just startups making noise, look at who is actually putting the money and the careers on the line. First one, Yanle Kun, turning award winner, chief AI scientist at Meta for 12 years. This is one of the most respected AI researchers alive. He left Meta, walked away, raised half a billion euros for a startup called AMI Labs. And his core thesis, which is a pretty bold claim, is that language models will never understand the physical world. They can talk about physics, sure, but they don't understand it. He thinks world models are the only part to real intelligence. Second, DeepMind. They released something called Genie 3 in August 2025. It is the first real-time interactive world model. You describe an environment in text and it generates a navigable 3D world at 24 frames per second. Real time, interactive, and it learned physics from completely on its own. Nobody told it about gravity or momentum. Third, NVIDIA and Dassault Systems at GTC 26, which was just weeks ago, they announced industry world models, enterprise grades, physics validated spanning from production design all the way through factory operation. So think about this for a second. Len Kun, DeepMind, and Jensen Huang are all independently converging on the same idea at the same time. In my experience, when the smartest people in the room all point in the same direction, that is usually a signal worth paying attention to. Let's shift our focus to a digital twin. So okay, before we talk about the world models, let me make sure we are all starting from the same place on digital twins, because there is a lot of confusion around this term. A digital twin is not, and I want to be really clear here, it is not just a 3D model. I see this misconception everywhere. Someone renders a factory in 3D, puts it on a screen, and calls it a digital twin. That is not a twin, that's a visualization. A real digital twin has three things. First, live data. Sensors on the physical asset are continuously feeding data into the virtual model, not once a day, continuously. Second, it is bidirectional. The physical world updates the twin, yes, but the twin insights can also drive changes back in the real world. That two-way communication is what makes it a twin and not just a one-way mirror. Third, it enables simulation, prediction, and optimization across the full life cycle. What do companies actually use this for? Four big buckets. predictive maintenance, predictive failures before they happen, which can put unplanned downtime up to 50%. That alone is worth millions for most manufacturers. Production optimization, testing changes to a line in simulation before touching anything special. Quality control, catching defects in real time, and supply chain visibility, simulating what happens when a supplier goes down or demand spikes unexpectedly. Really powerful. But, and this is important, there is a ceiling, and that ceiling matters more than most people realize. The ceiling of digital twins. So here are the four things that nobody talks about at the key vendor keynotes. These are the things I want to know. Number one, digital twins are rule driven. That means somebody, usually an expensive domain expert, has to sit down and manually encode all the physics, all the equation, all the boundary conditions. That takes months. And if there is a scenario they didn't think of it, the model doesn't cover it. It is blind to anything, and wasn't explicitly programmed for. Number two, they are expensive. We are not talking about a weekend project. A single factory level digital twin can cost millions of dollars to build, and then more millions to maintain year after year as things change. For most company, that is a serious investment decision. Number three, they are brittle. Here is what I mean. Everything works great as long as the real world behaves exactly the way the model expects. But the moment something changes, a new material, an unusual temperature spike, a machine that vibrates differently after maintenance, the model breaks. It wasn't designed for that scenario. And number four, zero generalization. Everything you build for one machine, start over for the next one. All that engineering effort can transfer it. Can't reuse it? Every new asset is a blank slate. Now just hold on those four into your mind for a moment, because every single one of them is something world models are significantly designed to solve. Rule driven, world models learn from data, and it is expensive. They transfer across domains, so you don't rebuild from scratch or brittle. They adapt to novel condition. No generalization. Generalization is literally their superpower. Let me go to some use cases. Let me give you a real example of digital twins working well before we move on. Because despite those limitations, when they are done right, they are incredibly powerful. BMW, they build 2.5 million cars every year. That's a lot. But there is the thing that makes the manufacturing insanely complex. 99% of those cars are customized by the customer before purchase. Different color, different interior, different features. Almost every car coming off the line is slightly different from the last one. So, how do you manage that complexity? They use NVIDIA Omniverse. They simulate their entire factory operations, the layout, the robot movements, the material flow, the logistics across more than 30 factories worldwide. Teams in Munich and in teams in South Carolina can work on the same virtual factory at the same time. And the results, what used to take years of factory planning, now takes weeks. That's not a small improvement. That's a fundamental change in how fast they can move. And here is where the money is. When they want to reconfigure a production line that used to mean months of shutdown time and hundreds of thousands of dollars in physical changes, now they test 10 different configuration, digitally pick the best one, and only build that one shot done right. Let me move to the next use case of Foxconn. Different example, completely different domain. Foxconn, the electronics manufacturing giant. The big challenge, thermal management. In electronics, manufacturing heat is the enemy. Chips overheat, circuit boards develop thermal stress, soldier joints fail. And the absolute worst time to discover a thermal problem is after you have already manufactured 10,000 units. That's an incredibly expensive problem to fix. The traditional approach was computational fluid dynamic simulation. Works well, but takes days to weeks for a single thermal analysis. But takes days to weeks for a single thermal analysis. And because of that time constraint, they could not only test maybe 5 or 6 scenarios before they had to commit to a decision and start production. After deploying Cadence, Reality Digital Twin platform with NVIDIA Omniverse, 150 times faster. Let that sink in for a second. What took a week now takes under an hour. This means instead of testing 6 scenarios, they can test 600. And the most important thing, they catch thermal issues before production starts. Not after. The difference between a 5 minute design and change and $1 million call. Let me move to the notebook. So this is the physical machine like industrial motor simulation. So we have simulated a three-phase industrial motor with sensors for like temperature, bearing heat, vibration, mechanical health, RPM, rotational speed, and current draw electrical load. So the motor degrades over time. The digital twin must track this. So this is like a Pythonic script I have written it, and then I won't go much into the code, but I'll explain the what are the crux for it. So this is the physical model with initial readings, temperature, vibration, RPM, current, health, and hours. So next is like the digital twin, like the virtual replica. The twin mirrors the physical motor and adds state estimation, which tracks internal health from sensor data, and anomaly detection flags when readings deviate from expected. Remaining useful line RUL prediction. Let me run the factory with physical plus digital twin side by side. We'll simulate 8,000 hours of motor operation, so which is approximately 1 year, and watch the twin track degradations in real time. So this is the digital twin dashboard, which talks about the industrial motor life cycle. So this is all the simulated work. So it's not all the real use case what I have developed for, but I just wanted to give you what basically like digital twin stands for, and then how we can use into our business case. So simulation was completed with 8,000 hours of operation, and then final motor health was like 16.71%. It also shows you like the first alert was raised at like 44,000 4,400 hours, and early warning gave over like 3,600 hours of advance notice, and failure mode was like bearing failure, so it also gives you what type of mode, and then the total alerts raised was 37. So this is basically on like each and every different use case. So this is just for like I have created for like industrial motor life cycle, but you can take this example and then think about from your perspective how you can think about the digital twin. So that's where like I wanted to bring to your notice. And next is like the virtual texting, the Foxconn like 50,000 speed up. So like digital twins let you test hundreds of scenario virtually instead of waiting for real world results. So let's simulate this testing with 100 different operating condition to find the optimal load factor. So like motor life versus loading load, and then the peak temperature versus the operating load. So 100 scenarios were tested in 0.05 seconds, and like which the real world equivalent was like 85 years of motor operation. So that is like 85 years compressed into less than 1 second. So optimal load factor was like 0.50. So lifetime, which was like 16,000 hours. This is why Foxconn achieved 15 times faster testing with digital twins. Next is like the BMW scale, like which is the multi-asset factory twin. So we have designed like BMW twins with 30 plus factories. Let's simulate a small production line with 5 machines and show how the twin monitors fleet health. So this is the graph between like time steps in 100 hours and estimated health. And then this is like number of alerts, and then like what is the maintenance priority. This gives you the fleet status summary. It also talks about like machine health alerts and actions needs to be taken. So these are like all the problems like I took into consideration based on the real world use cases, but the data is like more on simulated side. Let me move back to a PPT. So let me go to what is a world model. So we have seen what digital twins do well and where they struggle. Now let me give you a proper clean definition of what a world model actually is, because I think precision matters here. A world model is a neural network that learns an internal representation of how the physical world works. And this is the key, purely from data. Nobody programs the physics, nobody writes equations. The model observes the world and builds its own understanding. Four things make world model fundamentally different from anything we had before. First, they learn physics from observation, not coded rules. Observation second, they generalize something the model learned about fluid dynamics in one industry can transform to a completely different industry. Third, and this is one that really gets me, they can imagine, they can create scenarios. They have literally never happened. not in interpret from past data, genuinely novel scenarios. And fourth, they serve as the brain for AI agent. An agent can use the world model to think ahead, plan actions, predict consequences before acting. Here is a simple way to hold this. A digital twin is a mirror. It reflects what already exists in the real world. A world model is an imagination. It can dream up what doesn't exist yet, what might happen, what could go wrong, what will change if you did something differently. That's a fundamentally different capability, and it's why I'm so excited about this space. Let me put them right next to each other because I think this comparison is the most important thing to take it from away from today. Digital twin, it mirrors one specific system. It's rule driven, needs manual calibration, needs constant sensor data. And the question it answers, what is happening right now? World model. It learns from data, it generalizes across domains, it can imagine novel scenarios, and the question is answers. What could happen? But here is what I really want you to walk away with. The future is not one or the other. It's not a competition. They work together. The digital twins gives you ground truth. What is actually happening on your factory floor right now, based on real sensor data. The world models gives you imagination. What will happen if you change this parameter? What could will break if that supply went down? What's the optimal configuration you haven't thought of yet? Together, you get both. You monitor what is and you predict what could be. And that combination is more powerful than either one alone. So here are the four big shifts defining this transition. Let me walk through each one quickly. First, we are going from replication to abstraction. Instead of trying to perfectly copy every bolt and wire in a physical system, world models learn compressed representation that capture the essence of how things work. They don't need every detail. They need the right patterns. Second, from rule driven to data driven. Instead of engineers spending months writing physics equations for every scenario, the AI just watches data and learns the physics itself. Massive difference in speed and adaptability. Third, from passive simulation to active imagination. This is a big one. Traditional digital twins can only simulate scenarios they were programmed for. World models can generate scenarios nobody showed them, novel situations, edge cases, things that haven't happened yet but might. And fourth, from system centric to agent centric. Instead of a system that humans query and monitor, we are moving forward toward AI agents that use the world models as their brain. They can reason, plan, actually take action within the model. And if you zoom all the way out, this is a 30-year evolution. Rule-based system in the 90s, machine learning layered on top in the 2010s, AI-powered digital twins around 2018 with BMW and Siemens going big. And now world models. Each stage didn't replace the one before it built on top of it. And I think that pattern will continue. Okay, this is the part that honestly blows my mind every time I think about it. The traditional approach. An engineer sits down and writes equation F equals to ma. Navier-Stokes law fluids, Fourier's law for heat transfer, and every new scenario, new material, new temperature range, new geometry requires more equation, more manual work, more time, more expense. World models do something completely different. You take millions of hours of videos, factory footage, sensor data, simulation recordings, and you train a neural network on all of it. The model watches objects fall and discovers gravity on its own. It watches surface, interact, and learns friction. Nobody programmed any of this. The physics emerges from the data. And here is the beautiful thing. This is the exact same journey we have already seen play out in the domains. GPT was the foundational model for the text. Stable diffusion was the foundation model for images. Morai was, which we covered in my last data hour section, was the foundational model for time series. And now Cosmos and Genie 3 are the foundational model for physics. Same principle every single time. Train on massive data, learn general representation, fine tune for specific tasks. It worked for language, it worked for image, it worked for time series, and now it is working for physics. You know how a child learns gravity, not from a textbook, not from equation. They watch things fall over and over until they just know how the world works. World models learn exactly the same way, and I think that's beautiful. Let me take you under the hood for a minute because I think understanding the architecture makes this more concrete. Genie 3 has three components, and once you understand these three pieces, the whole thing clicks. First piece, a video tokenizer. It takes raw video frames and compresses them into discrete tokens. Think about how GPT works. It takes words and turns them into tokens that the model can process. Same concept, but for video. Continuous visual data gets turned into a sequence of discrete representation. Second piece, a latent action model. This one is really clever. It looks at two consecutive frames, frame 1 and frame 2, and figures out what action caused the change. Did an object get pushed? Did gravity pull something down? Did something rotate? It infers the action without anyone labeling it. Nobody tells it, this is gravity. It works it out from the pattern. Third piece, a dynamics model. Given the current state of the world, plus the inferred action, it predicts what the world looks like one step into the future. At interference, at inference, when you are actually using it, you give it a text prompt, describe a scene, and it starts generating frame by frame, auto-regressively. Each new frame feeds back into a generate the next one. At 24 frames per second, real-time interactive navigable 3D worlds. And I want you to really sit with this for a second. There is no physics engine in this pipeline. Anywhere, zero hard-coded rules, zero equation, everything the model knows about physics. It learned from watching. That's pretty remarkable. Next is like NVIDIA Cosmos follow the same exact recipe that made LLM successful. Same playbook, different domain. Stage 1. Data curation. You gather massive amounts of data, real world video, simulation data from Omniverse, sensor recording from industrial equipments, covering every kind of physics you can think of. Rigid bodies, fluids, soft material things with joints and hinges. The more diverse the data, the more general the model's understanding. Stage 2. Pre-training. You train a model, world foundational model across all that data. Think of this as your physics backbone, just like GPT's based model. Understands language in general. Before you tell it anything about your specific company, Cosmos understands physics in general. Gravity works, collision happen, fluids flow. It knows the basic of the physical world. Stage 3, and this is where it gets practical for companies, fine tuning. You take the general model and specialize it for your domain, your factory, your equipment, your processes. And just like fine tuning an LLM, you don't need enormous amounts of data. The base model already understands physics. You just need to teach it the specifics of your situation. Stage 4, deployment. Generate unlimited synthetic data for training robots. Run what if scenarios for production planning or feed better simulation back into your digital twin. The magic phrase, pre-trained general, fine-tune specific. That's the exact formula that made ChatGPT work. And it's the exact formula that makes Cosmos works for physics. That is why I keep calling this the GPT moment for the physical world. Let me switch to the notebook. So this is the world model learns physics from data. So this notebook will demonstrate the paradigm shift from rule-based digital twins to data-driven world models. So rule-based physics versus learned physics, a neural network that discovers gravity from observation. Digital twins was world model comparison and ROI visualization from real deployments. Let me go to rule-based physics, the traditional approach. So engineers like manually code the equation what I have mentioned, F is equal to ma, heat transfer, fluid dynamics. Let's simulate a falling object with the hand-coded physics. So when you write an equation and then when you generate it, it looks something like in the graph it mentions. Okay, so this required an engineer to write the equation. What if the AI could learn this physics just by watching? Second, like the world model approach, learn physics from observation. Instead of coding F is equal to ma, we observe the system, collect the position or velocity data, train a neural network to predict next stage from current state. The network discovers gravity, drag and bounces on its own. We built a simple neural network from scratch, no PyTorch needed. So neural networks define three layers, similar like somewhere around like 2000 parameters, no physics equation anywhere in the code. So we get the training data like with 160 observation pairs. Like input is like position velocity at time t. Output is like position velocity at time t plus 0.05 seconds. Date range, something we have given. The network must discuss gravity, drag, and bouncing them from this data alone. This is the epoch, and the training was completed, and then it learned physics. Let me test the world model. Does it understand physics? We will let the trained network generates a trajectory from scratch using autoregressive predictions like GPT generated text. Here it is. So average prediction error is like 35.35 meters. So this is the honest assessment. This tiny model similar to 2000 parameters with 160 training sample captures the general trend, failing, bouncing, energy loss, but diverge over time. Errors compound with each autoregressive step, same challenge as LLM. So why this still matters? NVIDIA Cosmos use billions of parameters, trains on millions of hours of data. DeepMind Gen 3 generates photorealistic 3D physics at 24 FPS. The principle is identical. Scale is the difference between a toy and a production. So let me show you like the digital twin versus the world model. Let's test both approaches on new scenario they haven't seen and different initial height and velocity. It gives you the generalization test. So which perfect it has the equation. So world model approximate but learn entirely from data. At scale, Cosmos Gen 3 world models match rule-based accuracy while generalizing to scenarios the engineers never anticipated. Let me move back to this PPT. Next is, all right, this one is really important for anyone working with industrial data. So let me take a minute here. Factory sensors, vibration sensors, temperature sensors, pressure sensors, acoustic sensors, these things generally generate data continuously. A single sensor sampling at 1000 Hz, which is pretty standard, produces 3.6 million data points per hour. Multiple sensors running 24/7 across a production line. You're looking a billion of data points. Now, here is the problem with transformers. The attention mechanism, which is what makes GPT so good, computes relationship between every pair of elements in the sequence. That is a n squared operation. 1000 tokens, find a million operations, 100,000 tokens, 10 billion. A million data points, a trillion operations. For factory sensor streams, transformer just choke. Mamba takes a completely different approach. Instead of looking at every pair, it maintains what you can think as a running summary, a hidden state that gets updated with each new data point. And the update isn't fixed. It depends on the input. So when a significant vibration spikes comes in, the model goes. This is important. Let me remember this. When normal background noise comes in, it says, this is routine. I can let it go. Like human selective attention. You don't process every pixel in your visual field equally. You focus on what matters. The result, right? Linear scaling, 5 times faster inference, constant memory, no matter how long the sequence. And Mamba 3, which came out just last month, is a hybrid SSM layer for capturing long range patterns combined with attention layer for precision. IBM Granite 4.0 and AI 221 Jamba use the same hybrid approach. This is going to be the backbone architecture for the next generation of industrial AI. Let me switch to notebook. So this notebook will demonstrate why Mamba state space models matters for industrial AI. We'll compare the core operations of transformers versus Mamba on sequence of increasing length, simulating factory sensory data. A typical factory sensor consists of vibration, temperature, and pressure. Samples at like 1000 Hz. 1 minute is equal to 60,000 data points, and 1 hour is like and multiple sensors multiplied by 100 to 100x. Let's generate a realistic vibration signal. So you can see from the anomalic spike visible, this is what Mamba needs to selectively remember. Transformer cell attention, every tokens look at every tokens at 0 and square. Mamba SSM maintains a hidden states, update linearly. ON. Let's benchmark both core operation. So yeah, you can see it from the thing how different like the at different length transformer and Mamba speed up. So Mamba wins and the gap grows wider with longer sequences. Let me visualize the scale differences. So Mamba starts nearly flat for factory sensory data millions of point. Mamba is the only practical option. And like this is the real factory sensor data volumes at 1 sensor 1 second at like 1000 hertz, 1000 data point. One sensor at per minute is like 60,000 data points. At one sensor per hour is like 3.6 million. At 10 sensors 1 hour it's like 36 million. And 100 sensors 1 day 24 times 24 by 7 it's 8.6 billion. So transformer attention of 3.6 million points is equal to 13 trillion operations. And other on the other side, Mamba on like 3.6 million points is equal to 3.6 million operation. So that is why Mamba is the backbone for next generation industrial AI. And here is some like the predictive maintain anomaly detection on sensor data. So this sensor data we generally created like it has anomaly spikes, stimulating equipment issues. And this is like a real factory use this to predict before they happen. So which reduce the downtime up by 50%. This is all like like simple anomaly detector, and these are all simulated thing. So this is not the all the live thing. Okay, let me go back to PPT. Okay, this one is probably my favorite use case because it's not a research demo or a proof of concept. This is the real thing happening right now. Siemens and Nvidia are building the world's first fully AI-driven adaptive manufacturing site, the Siemens Electronics factory in Erlangen, Germany, starting this year, 2026. And here is how it works. They have what they call the AI brain. It is powered by software-defined automation combined with Nvidia Omniverse. The factory continuously monitors its own digital twin. When the AI sees an opportunity for improvement, it doesn't just flag it for a human to look at next week. It simulates the improvement, it tests it virtually, it validates the result, and this is the key, it pushes the validated change directly to the shop floor automatically. It does analyze, test, validate, deploy on repeat, continuously improving. So that's not a digital twin in the traditional sense anymore. That's the transition from digital twin to world models happening in real time at one of the world's largest industrial companies. Now let me shift to supply chain because this isn't just a manufacturing story. So Walmart is interesting because they are not explicitly building world models, but they are building the foundation for exactly that. They combine three types of data: shelf cameras that use computer vision for stock level detection, RFID tags for real-time inventory tracking across location, and transaction data that reveals purchasing patterns and demand signals. So they fuse all three into a unified intelligence system. The result, which is today, better demand forecasting, better inventory management, and an automated product category enrichment. So what you feed in the product image and out comes a description, tags, or like SEO optimized content. But here is where I think this is heading. All of that multimodal data fusion. So that's the stepping stone toward a full supply chain world model. One that can simulate disruption across their entire network, test responses before they are needed. Imagine scenarios nobody has planned for. The camera plus RFID plus transaction are building the data foundation. The world model is where it leads. Switch. Let me move back to notebook. So this is like a zero shot defect classification with foundational model. So no custom model, no label data set, no fine tuning, just a prompt and an image. So this is all like generate synthetic defect images. So it has like scratches, it has pittings, it has cracks, and it has inclusions. So these are all generated images. And then when you do with like zero shot classification with Claude API or anything, you can do like you can use OpenAI, you can use Gemini, any API keys, whatever you feel, and it does the analysis like scratches, like pitting, then cracks, and then it gives you the accuracy, and then it just like predicted, like misclassified, like predicted as inclusion. So synthetic image lack the texture detail on real factory image. Pitting and inclusion can look similar in low resolution grayscale. So on real world factory images, accuracy is typically 97 IIC benchmarks. So this is all like real world thing. And then this is the confusion matrix, what I got it. And the bigger picture, why this matters is, so Walmart combines multiple data sources for unified understanding, self cameras, so visual AI for stock detection, RFID tags, transaction data. So there is a stepping stone towards supply chain models. Let us simulate it. So the traditional versus foundational model approach. So this is the comparison, and foundational model doesn't replace all. But for many industrial inspection tasks, they are already good enough and they keep getting better with every model release. And then this is the multi-model data diffusion for a supply chain. It shows you how the product, the visualization, RFID, what is the sales, what is the risk. So no single data tells the full story. So camera sees shelf level, RFID tracks warehouse, transaction show demand, fused together is equal to predictive inventory management. So this is what a Walmart stepping stone towards supply chain models. Let me move back to PPT. And then there is what I consider the most ambitious example of all. At GTC 2026, just a few weeks ago, NVIDIA and Dassault Systems announced something called Industry World Models. And what I want to be really specific about what makes this different from a regular digital twin. This is a unified physics validated AI representation that spans the entire industrial life cycle. Not one phase, the entire thing: design, simulation, manufacturing, operation. One persistent AI brain across all of it. Lucid Motor is using this to accelerate EV deployment. The Bell Group, they make Babel cheese, among other things, is using it to simulate food protein development. And Nvidia itself, they use Dassault's tools to design and simulate their own AI data centers completely virtually before they break ground. Jensen Huang said on the stage that they run the network and the supercomputers inside the virtual twin before building the physical facility. So that's the future. Models that aren't one-time artifacts you build and shelf. They're continuously evolving system representation that grows smarter over time. So let me pause here and recap because we have got a lot of ground. 5 use cases: BMW, 30 plus factory digital twins, years of planning compressed to weeks. Foxconn, 150 times faster thermal simulation. Siemens, the world's first AI driven adaptive factory starting this year. Walmart, multimodal data fusion as a foundational for supply chain world models. And NVIDIA plus Dassault, industry world models spanning the full product lifecycle. And I want you to notice that progression here. You started with digital replicas, accurate mirrors of what exists, and we ended with AI that imagines reality, system that can dream up what could exist. The arc from replication to imagination is the whole story of today's session. So now here is where I want to be completely honest with you, because I think credibility comes from not just telling you the exciting parts. This is still early. Let's be real about what most of the production deployments we have seen at big tech companies or large industrial with massive budgets. Mid-sized company are still figuring out where to even start. World models can hallucinate. They can generate scenarios that look completely realistic, but are physically impossible for safety critical application. A jet engine, a nuclear plant, a pharmaceutical process, that's the real problem. You can't just trust the output blindly. Pre-training needs massive data. The base model, the physics, the backbone requires enormous data sets to train. Now, fine-tuning is lightweight, but someone has to build that foundation first. Regulatory certification. This one is big and nobody has a good answer yet. How do you certify a model that learns physics implicitly instead of being explicitly programmed with known equation? Regulators don't have a framework for that. And interpretability, when a world model makes a prediction, it is really hard to explain why. It just knows, but it can't show its work the way a physics equation can. These are real challenges. I'm not dismissing them, but I genuinely see them as an engineering problem that will be solved over time, not fundamental barriers. 5 years ago, people had the same concern about LLM. Today, we have frameworks, guardrails, and validation methods. The same thing will happen here. Let me move to notebook. So this is the limitation. These are the numbers from real deployments. So you can see how they are hallucinating and then what is how the ground truth is, and then world model challenges, few production deployment, moderate interpretability, safety certification, data hungry pre-training, hallucination. So models can generate physically impossible scenarios. So we just saw it, train on H is equal to 100M. It fails at 500M. Data hungry, massive data needs for pre-training. Fine tuning is lightweight, but the base model needs millions of hours. Safety certification. How do you certify AI learned physics from safety critical use? Example, like regulatory framework don't exist yet. Interpretability, hard to explain why a world model made a prediction. Unlike example, like it can be unlike rule-based models where you can trace each equation. Still early, few production deployments outside big tech companies, example Siemens and Nvidia leading, but most factories aren't there yet. So these are the real challenges, but they are engineering problems, but they are not blockers. So ROI from real deployments, you can see it from the screen. So ANSYS plus Omniverse, it's 1200x, Foxconn plus Cadence 150x, and traditional baseline. And inspection quality, AI versus legacy, all how AI inspection new is coming, and then what was the legacy system for the previous one, and then how the accuracy and then the false positives are there. And these are the operational, in fact, yields versus saving, typically for the factory. So these are in predictions. So they are results from production systems, but only few of the handpicks companies are doing it. Let me move to the slide. As you can see from the, like you have seen the ROI, the numbers. So all right. Because at the end of this day, this is what actually moves a decision moving in a leadership meeting. Simulation speed, ANSYS combined with NVIDIA Omniverse, 1200 times faster CFD simulation. So that's not a typo. It's 1200 times from their own published benchmarks. Foxconn, 150 times faster thermal analysis from Cadence case study. Quality and defect detection, AI-powered inspection system hit 97 to 99% accuracy. Now compare that to legacy automated optical inspection, which typically has up to 50% false positive rate. That means half of everything it flags isn't actually a defect. AI brings false positive down to 4 to 10%. Think about how much time and money that saves in manual reviews alone. Then the operation sites, more than 3,100 hours saved per application per month from reduced manual inspection. A yield improvement of just 0.3 to 1% sounds tiny, but at high production volumes, that translate to millions in actual savings, and predictive maintenance can cut unplanned downtime up to 50%. And the last, the invested trend, 55% of manufacturers are planning to invest over $100,000 in machine visual technologies in the next 2 years. So that's from the ABI research. These are not production numbers from the slide deck. These are real numbers from real companies in real production. So the ROI is proven. So this is the fact. This is the past the experimental stage. So what's the technology stack that makes all the possible? Four pillars. First, NVIDIA Omniverse and OpenUSD. So Omniverse is the platform. OpenUSD is the universal format. Think of it as a PDF of 3D. Before PDF, sharing documents across software was a nightmare. OpenUSD does the same thing for 3D data, Siemens data, Dassault data, Autodesk data, all speaking the same language. Over 300,000 downloads created by Pixar, adopted by Apple, NVIDIA, Adobe, and the rest of the industry. Second, world foundational model, Cosmos and Genie 3, AI that learns physics from data. This is the imagination layer. Third, Mamba and state space model for handling the long continuous sensor stream that factories generate, linear scaling, constant memory. So this is what processes the millions of data points your sensor produce. And fourth, multimodal foundational model, GPT 4.0, Gemini, Claude for tasks that require understanding of images plus text plus structured data together, defect classification, report generation, catalog enrichment. And for deployment, most production systems use a hybrid architecture. Edge devices on the factory floor handle real-time inference, sub-second latency, data stays on premise, important for data sovereignty and regulation. Cloud handles the heavy lifting, model training, world model simulation, synthetic data generation, edge for speed, cool for scale. That's what the production look likes. And let's move to the big question. You're sitting here thinking, okay, Ankit, this is fascinating, but how do I actually start? So, 4 steps. And please, for the love of everything, don't skip the first one. Step one, data readiness. I know this isn't good, but nobody gives a keynote about data cleaning, but it is the foundation for everything else. If your sensor data is messy, if your teams are working in silos, if you can't stream real-time data from the shop floor, fix that first. Seriously, I've seen companies spend millions on fancy platforms and then get garbage results because the underlying data was a mess. Step two, start small, pick one machine, one asset, build a component, when something focused where you can clearly measure the before and after, and then prove the ROI. Show leadership a number, not a demo, a number. Step three, once you are have proven it works, let it go expand, go from one machine to full production line, a composite win. Step four, graduate to a world models, AI that learns your physics and can generalize across your operation. For platforms, NVIDIA Omniverse if you need simulation and physical AI, Siemens Accelerator if you are already in the ecosystem, Dassault 3D experience for design and engineering. Pick based on what you already have. Don't rip and replace. All right, let me bring it all together. 5 things to walk away with. One, digital twins are powerful. They have delivered real value at BMW, Foxconn, and many others, but they have a ceiling. They are rule driven, expensive, brittle, and don't generalize. Second, world models break through that ceiling. They learn physics from data, they generalize across domains. They imagine scenarios nobody anticipated. Three, this is not theoretical. BMW, Siemens, Nvidia, Dassault, they are deploying this technology right now in production, not in the lab. Four, the tech stack is ready. Omniverse, Cosmos, Mamba, multimodal LLMs. These aren't research prototypes, they are available today. Five, the path is clear. Start with data readiness, prove value with a component win, scale to composite wins, graduate to world models, don't skip steps. And looking ahead to 2027 and beyond, autonomous factories powered by world model agents, robots that are trained entirely in imagination before they ever touch a physical object, and the grand convergence of state space model, world models, multimodal AI, and agentic system all coming together into something much bigger than any one of them. And I will leave with one thought. The question is no longer if this will happen. The evidence is overwhelming. The question is how fast your organization decides to move, and the organization that starts now. They won't just adopt this technology, so they will define it. They will define what the next decade of manufacturing industrial operation looks like. So thank you for all staying with me throughout the whole session. Really appreciate your time and attention. I'll share the slides and resources a link after the session. And like one more keynote is like, so this is the ongoing thing for like Mamba, Cosmos, Omnisys, everything. So we have to keep on working, keep on understanding how things look, how things are basically experimented, learn, walk, like go over the research papers, understand, and then think about it, and then you put it into picture. That's all I want to say. Thank you.
Before we answer any questions you guys have, I request everyone to fill the feedback poll also.
One thing I will suggest is like go over the archive papers of Mamba and StageSpread's model. Then you'll have like more clear picture how this will really impact the real world.
Okay, if there aren't any questions now, thanks a lot, Ankit, on behalf of Analytics Vidya. Thank you for your time and delivering such a wonderful session. Our audience must have found it insightful. I hope everyone has filled the feedback poll. If not, please do so, as your feedback is valuable, as it helps us to conduct more such sessions like that. And the recording of the session will be available within 2 days on our community events platform page only. And we'll be back with another session of data art session soon. The link of the upcoming session will be available on our events page. Till then, bye bye. Have a nice day and a happy
Thank you.
weekend.
Thank you.
Hi Ankit, are you there?
Yes.
Ankit, I guess there is one question in the Q&A if you can see.
I'm not able to see anything. Yes, automatic research will be a future for AI. Yes, because everything we are moving, and then like different models are coming into picture. So yes, for sure, like automatic research will be the future space for AI. Basically in factories, manufacturing unit. Yes.
Okay, great to have you guys. Have a nice day. Bye bye.